worked as a senior scientist for U.S. Geological Survey, Columbia University, UNEP, and Asian Institute of Technology, and Forest Department of Nepal. His research is to map and monitor mangrove forests and work to identify rates, pattern, causes, and consequences of mangrove change. Dr. Giri, time is yours.
Thank you for the introduction. And after the excellent presentation by Professor Sunny, I would like to take you to the world of remote sensing. Here I'll be talking about mapping and monitoring of the mangrove from local to global scales. First of all, I would like to acknowledge my collaborators, NASA, USGS, United Nations Environment Program, and the Duke University. So, a lot of people ask me, why do you want to map mangroves? And there are a number of reasons, but I have highlighted three main reasons. The first thing is that we need information for decision making. And here we are talking about restoration, conservation, and sustainable management, and we need information for that. So we want to know where the mangroves are, what the conditions are, how they are changing, and what is the species composition, and so on. And for that, remote sensing can play a very important role. It cannot solve all the problem, but remote sensing provides important information. The good thing about remote sensing is that mangrove has a very distinctive signature. This is a false color composite of Landsat data covering the largest remaining tract of a mangrove forest in the world, in the border between India and Bangladesh. The dark red color is mangrove, and it's very easy compared to many other land cover classes to map and quantify these mangrove areas. At the same time, remote sensing technology is developing very, very fast. And on your left, you can see a number of Earth-observing satellites orbiting the Earth. These are only a few satellites. There are many others. And if you look at the upper right slide, in 1972, there was only one country, USA, had launched the satellite and started collecting the data. But if you look at now, there are more than 37 countries who launched their own satellites and collecting the data for their natural resources management. In the lower right slide, you can see that the digital volume, the data volume that we archive in the world has increased significantly after 2005. Until 2005, it is relatively low. But after 2005, you can see the data volume has increased. And this trend is likely to increase in the future. So we will have lots and lots of data to work with. Another important development happening in remote sensing is small satellites. For example, Dove and the SkySat satellites. Those are small satellites. SkySat satellite was previously owned by Google, but now it's owned by a venture capital fund, a company called Planet Lab. So you see that the land to develop and launch satellite, it cost $1 billion. And the size of Landsat satellite data is maybe the size of a car. But now we have small satellite. The SkySat is maybe the size of washing machine, and then Dove is the size of a shoebox. And the other thing is the cost of these satellites is very, very low. It could be in like $10,000, $20,000, or $50,000 range, not in billions. And the other thing is, in case of Dove, they are launching the satellite in flocks. They are launching 32 satellites at a time. So basically, right now we have hundreds of satellites in orbit. And the goal is to observe the Earth at 3 to 5 meter resolution every day. Similarly, we have data coming from drone as well as low-cost sensor technologies. And the involvement of citizen science is also playing a role in providing the data. The other thing, at the same time, we have lots and lots of data, but the information technology is also improving. And when I started my career, the data storage was a big problem. But now we can store the data in cloud, and we don't have any limitation to store the data. At the same time, computing has become so powerful that we can send our analysis to hundreds and thousands of computers and then get back the results. So cloud computing is also improving. And then some of the example I have is Google Earth Engine and Amazon Web Server. Now, with all the motivation, a few years ago, our team prepared the global mangrove database. And this is based on Landsat 2000 datasets published in 2011. And before that, we had global datasets on mangrove, but they were inconsistent over space and time. And this is the first time we prepared the most comprehensive and globally consistent global mangrove datasets at a 30-meter resolution. If you look at a local scale, this is a map of the Guinea-Bissau. This data set can be used at a global scale as well as national scales or even local scales. It's very detailed at 30-meter resolution. Based on this, we calculated some statistics, and you can see that Asia has the highest amount of the mangrove, 41%, followed by Africa and North and Central America. I also tried to look at the area distribution by country, and you can see that Indonesia has the highest percentage of the mangrove, which is like 22.6%, followed by Australia and Brazil. Between Australia and Brazil, the difference is not much. The interesting fact about this graph is, the lower graph is that these 15 countries constitute 75% of the mangroves of the world. And then the top slide shows that how the mangrove is distributed in different latitudes. We divided the distribution into 5-degree latitudes. And as expected, you can see that most of the mangroves are found in tropical and subtropical region, and mostly within plus minus 10-degree latitude. And the distribution is a little bit biased towards the northern hemisphere. We have more mangrove in northern hemisphere than southern hemisphere, and the latitudinal range can extend all the way to 38, 39 degrees. This data is freely available from a number of sources. I have mentioned half a dozen sources here, but there are maybe other, more than a dozen other sources that you can freely download. The data is available in both raster as well as vector format. Now, next thing I want you to do is look at the change. Change capturing both natural changes as well as anthropogenic changes. Here is an example of one of the islands in Sundarban. We have time series satellite images, and then through time there was erosion, we lost the island, and at the same time we lost the mangrove. Another example here showing the aggradation, where because of the sedimentation, the land area has increased, and in the process we also gain mangrove areas. And here, not one but multiple factors are in play. And the red areas are mangrove, but because of the winter freeze, they were killed and they started recovering again. They were killed and started recovering again. But by the year 2010, we lost the whole island. So again, we lost the mangrove. So some of the example of the anthropogenic changes. This is again time series images in Honduras. This is before the shrimp farming cultivation started here, and this is how it looks like in the satellite image, the Landsat satellite images after the massive introduction of the shrimp farms. This is another example showing that historical time series data plays very important role in monitoring the mangrove. The good thing is that for the Landsat we have data all the way to like 1972. We can go back and look at those historical data sets. If you look at this slide here, lower slides, in 1983 there was a lot of mangrove, and then 1984 there was a major winter freeze and all the mangroves were killed. You hardly see any red areas, the mangrove areas in the 1984 image. But by 2020 all the mangrove areas were restored. So one of the important things I want to highlight here is that if we do two-time analysis of 1984 and 2010, you can conclude that mangrove is expanding. But that is not true in this case. So there was a paper published in PNAS, and then we published a rebuttal showing 1983 image. So a lot of time we conclude very easily, but we have to be very careful and try to look at as much data as possible. Here we did a quick and dirty analysis a few years ago for an international meeting, and in Carpathia in northern Australia, mangroves are expanding. If you look at the graph here, overall the mangrove is expanding. In a lot of cases, mangrove expand either seaward or landward, but in this case, the mangrove was expanding in both directions. And this is the picture of those mangrove areas. But just last year, all of those mangrove areas died. There's a very nice paper published by Norman Duke that explains why those mangrove areas were killed. But it looks like mainly because of the drought and some other related factors. And again, looking at the change after the Asian tsunami, we wanted to know where the mangroves are and how they were changing, whether they can play any role in saving lives and property from natural disasters such as tsunami or not. So we did this change analysis covering just the tsunami impacted region of Indonesia, Malaysia, Thailand, Myanmar, Bangladesh, India, and Sri Lanka. We didn't cover the entire country of Indonesia, Malaysia, Thailand, just those impacted regions. First thing we noticed is that despite a very high population density in India and Bangladesh, the Sundarban mangrove forest area has not changed that much. There are some changes in the Indian side, but in terms of the total area, it has not changed that much. But the major change we noticed was in Myanmar. A lot of deforestation, mainly due to the encroachment. And we also tried to look at what are the major causes of the mangrove in these areas. And it seems that for this particular area, agriculture and the stream farming are the major causes. But in Malaysia, urban development is also playing a major role. And then those are the aerial changes. Then we also wanted to look at whether we can use remote sensing for mapping the species composition. We did this exercise in southern Thailand and tried to map not the single species but a group of species. And we got a very good result, and the paper was published some time back. um, the idea is to expand this to other parts of the world. So our group is also looking at LiDAR data. LiDAR provides information on a three-dimensional view of the forest, and that can be used for estimation of biomass. Here we can directly measure some of the parameters like tree height and canopy cover and that sort of thing, and we can extrapolate that to bigger areas. This is the work by one of my colleagues, Mark Schimart, who uses subtle radar topographic mission, digital elevation model, and derive the biomass of the forest in this case, Everglades National Forest in USA. So one of the things that I wanted to look at is like, we did 30-meter mapping, but it does not capture small patches of the mangrove forest. So we really wanted to use high-resolution data, like 2 to 5 meter resolution. And we did a comparative analysis of Landsat and big bird satellite data so that we can capture the small patches of the mangrove. This is an example where we did every 5 years of analysis in Florida and calculated the statistics. And you can see that in 1990, there was way less mangrove areas. And that is not because the mangrove area had changed. That was just a temporary. So this graph tells us that although we did 5 years of monitoring, but that 5-year interval is not enough. So we started looking at stacking together every Landsat images acquired every 8 days or 16 days, and look at the NDVI profile. And if we smooth that a little bit, we can see that there was a healthy mangrove, and then all of a sudden, a mangrove died because this is because of mangrove die-off. So this we can identify those areas. And here is another example where there was a disturbances, mangrove died, but it recovered quickly. So basically, we are trying to come up with this kind of framework where every time, whenever we get the data, we get satellite data every day. So as soon as we get the data, we plug in the data and then identify where the change areas are, and then at the same time, at the right-hand side, map the mangrove database. So it's a near real-time change analysis of the mangroves. So these are some of the ongoing activity they're working on. We're working on updating the 2000 mangrove database for 2015. And then one of the things that we want to do is identify the mangrove change area from 1985 to present on an annual basis. And a few other things we want to do is expand its mapping of the species composition, height, health of the mangroves, and so on. And then ultimately, from 30 meter, we want to move to the high resolution, like 5 meter resolution mapping for the entire world. And this was, again, I think this is provides summary of all my slides showing that this is possible because the demand for information is increasing, satellite and ground data availability is increasing, image classification methods improving, IT technology is improving, even remote sensing technology is improving, and the experts, we have more experts than before. Just 2 quick slides here. Last year, I edited, I was a guest editor for this special issue of remote sensing where we highlighted remote sensing of mangrove forest. There are 12 papers. This is open access journal. And I'm involved in some of the international initiative mentioned here. We have GEO, Group on Earth Observation, Mangrove Monitoring Group, which I led. And then we have Blue Carbon Scientific Working Group. We have a few parents here involved in that one. Daniel is involved in this one, and a few other activities. And that's all. Thank you very much.
Presentation will be